Welcome back. So we're going to do two examples. This one, example 3 and example 4. Um, they're related to each other, and there's several common themes or elements. So we'll go ahead and transfer this. All right. So this is example 3, which is a transformation from R2 to R3, and t of x was given by this relationship here: x plus y, x 2x minus 2y. So we're looking for the matrix that represents t. Okay, so we're going to try and figure that out. And so an easy way to really think about this is um, the transformation of the unit vector. In this case, if we're looking at R2, where does the map, if I map t into I, where does that get mapped to? Okay. And likewise, t of j hat, if I look at where does that get mapped to? Okay, and if I can answer where those get mapped to, then that can help me figure out what the matrix T, the matrix associated with this transformation T is. Okay, and this is true of any matrix, but the nice thing about I hat and j hat is that, of course, they're both unit vectors, but also one of their components is 0. So that's very helpful. Okay, so let's look at this transformation and see what happens. So T times I hat, what does that equal? Well, that's T times 1 comma 0. That is the transformation. Those are the components of I hat. And so what does that give us? Well, that gives us 1 plus 0, 1, and 2 times 1 minus 2 times 0, which of course gives us 1, 1, and 2. Okay, so this is exactly the same thing as the first column of our transformation matrix A. Okay, so this is going to be the first column, and this is what's going to happen to, and that's what happens to I hat. So let's figure out again what happens to J hat. Well, what is that? Well, that's the transformation of 0 comma 1, which is going to equal 0 plus 1, 0, and then 2 times 0 minus 2 times 1, which is going to give us 1, 0, and negative 2. Okay, and this is nice because then that tells us then that the second column of our transformation matrix, A2, or the second column of the matrix A. So let's see. So putting these two together, then it looks like our transformation matrix is going to be 1, 1, 2, 1, 0, negative 2. Okay. And let's just verify that, in fact, that is the case. So let's take our transformation matrix, A, and we're going to multiply it by a vector x. So what do we have? We have 1, 1, 1, 0, 2, negative 2. And multiply that by vector xy. And if we do that, we get x plus y, we get x, and we get 2x minus 2y. And so that checks. That's exactly what the transformation matrix was. Okay, and you should see then being able to identify that the transformation matrix is in fact you can almost pick it off just by looking at the form of the transformation. Okay. All right, let's go ahead and jump into the next one and see how. All right, so as I was saying, this is example 4. This is number A. And so in this problem, we have a transformation from R2 to R3 given by this relationship. And so we're trying to figure out what happens to the vector v1 equal to 1, negative 2, and the vector v2 equal to 3, 2. Okay, so we're trying to figure out the transformation of these two. All right, so to do that, we just go ahead and apply the transformation. Okay, so t of 1, negative 2, this is for v1. What does that equal? We have 1 minus 2, 1, and 2 plus 2. And so that means that our transformation for t of v1 is going to be negative 1, 1, 4. So this transformation takes the vector 1, negative 2 to 1, negative 1, 1, and 4. Okay. All right, let's try the transformation of vector 2, which is, I guess I should have written that here, v1, which is going to be the transformation of 3, 2. And so it's going to give us 3 plus 2, 3 and 6 minus 2. Okay, so that's going to be 5, 3, and 4. Okay, and it'll be the transformation then of our vector v2, which is 3, 2. It gets transformed to the vector 5, 3, 4 under this transformation. Okay, all right, let's go ahead and move on to part B here. B is the transformation. So S is a function from R2 to R3. And S is defined by the relationship x minus y, x plus y, and 2y. And then we have another transformation here, T from R3 to R3. And T of x, comma y, comma z is given by x, 2x minus y, and y, oh, sorry, I guess it's an x plus z. Okay. And it wants to find the matrices. So we need to find S, T, and then the composite one, TS. Okay. Okay. So from our previous example, it should be pretty easy to see. We could multiply by the corresponding unit vectors I hat and j hat and see where this goes, or we can just kind of recognize that for S, by inspection, that's going to have the values 1, -1, 1 and +1, and then 0 and 2. Okay. Likewise, T is going to have the components 1. Hold on. Keeping the inspection going, we'll have 1, 0, and 0. Since there's no x or y, sorry, no y or z in the x component. Here we have 2, -1, 0. Here we have 1, 1, and 1. Okay. All right. And so to compute the composite matrix of TS, we have product of this matrix and this matrix. Well, this is a 3 by 3, and this is a 3 by 2. And so the product of a 3 by 3 and a 3 by 2, since those are compatible, it's going to produce a 3 by 2 matrix. So it is compatible, which is good to note that, or you should note that ST is not a composite matrix. This does not exist. Do you see why? Based on the dimensional analysis, it should be clear. So anyways, if we multiply these two matrices together, T and S, what we would get out of that, thanks to the magic of GeoGebra, is 1, -1, 1, -3, and 2, 2. Okay. Just to confirm that, let's jump over to technology real quick, and we will show that. Okay, so here we have S is equal to 1, -1, 1, 1, and 0, 2. There's a matrix S, and our matrix T is going to be 1, 0, 0, 2, -1, 0, and 1, 1, 1. Okay, so TS, opening it out, is 1, -1, 1, -3, and 2, 2, just like we suggested in the calculation from previously. I just want to show how you could calculate it in GeoGebra using the tool. All right, hope that was helpful. And now let's move on to part C. Welcome back, everyone. So on this part, doing part C, we have the same matrix. We want to compute T squared times S. So we'll just use technology to do that, since we already have those defined. So we're going to look at T squared, just so we can kind of get an example of what that looks like. So there's T squared. And then if we take M2, which is T squared, times S, times S, S, we end up getting this is our result. So this is t squared times s. We get 1, -1, 1, 1, 4, and -2. Okay, and so to write the formal definition, we'll jump back over to write that on paper. But that's the quick way of using technology to determine the value of the uh, that transformation. Okay, so now that we're back here, so for part C, we wanted to compute t squared s, and we got that equaled 1, -1, 1, 1, and 4, -2. Okay, and we want to write this out formally. So this is a map from, so just like what we did up here, the formal, when it says formal mapping, this is what it's referring to is how do you write out each of the matrices. Okay, and so it's asking what are you working on or opting on first, and so it is written left to right, but we are acting right to left. So S is going to be the same R2 to R3. Okay, and then T is also going to be a map from R3 to R2. To R3. I was looking at the square on the T. So R cubed to R cubed. And so this is our map, R2 to R3, and then R3 to R3, and it's given formally by T of X, Y, and Z as, we don't have enough room to squeeze it in there. Also, I'll write it down here. We have X minus Y, we have X plus Y, and we have 4x minus 2y. If we put all this together, so this is a t, so let's call this a new transformation. No, I should probably call it like t prime or something. That represented. Let's go with q. So we start with R2, so we're going to call it q, and that's going to be a map from R2 to R3. Okay, so that's our map, and then q of x and y is going to be given by, it's going to be given by what we had here, x minus y, x plus y, and 4x minus 2y. Okay, so this is the formal mapping or definition, if you will. It's a composite definition, but where we started from and where we're going to, and how are we getting it? It follows this relationship. Okay, all right. I hope that was helpful, and we'll jump down now to example D. Okay, and so example D was asking about the transformation T from R3 to R3, and it's given by the relationship of T, X, Y, and Z of X plus 2Y minus Z, 3X minus Z, and Y plus Z. Okay. Describe the transformation. So we want to look at T squared minus T, no, 2T squared minus T plus 3I. Okay. So we want to write this as a single matrix and figure out how to compute that. All right, so let's go ahead and jump over to technology to compute how to solve this. Okay. All right. Since we have the same, oh no, we have a new matrix. So let's go ahead and get rid of these. and build a new matrix. So T and call it T, and it's equal to 1, 2, -1. And then we have 3, 0, -1. And we have 0, 1, 1. Okay, so there's T. And then we want to calculate 2 times T squared minus T plus 3 times the identity 3. Okay, let's see, identity 3. Okay, and so now we have the identity matrix there. We have 2 times T squared minus T plus 3 times M1. Okay. All right, so there is our resulting matrix. That is the transformation that we were looking for. And we can formalize that discussion with the final result. So let's go ahead and jump back to the paper here and finish this last example. Okay. All right. So we saw that this map transformation is equal to 16, 0, -7, 3, 13, -7, 6, 1, 2. Okay, which we can then write as we'll call it Q again, of X, Y, and Z is given by 16X minus 7Z, 3X plus 13Y minus 7Z, and 6X plus Y plus 2Z. Okay, all right. I hope that was helpful on that bit there. And let's go ahead and look at the last example to finish up this lesson.